Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of basic electrical and electronics engineering. We'll dive into key concepts like laws of electromagnetic induction, direction of induced E.M.F. Slide 1. Faraday's laws of electromagnetic induction. Let's start with the fundamental laws that explain how electricity can be generated using magnetism. These are Faraday's laws of electromagnetic induction. Faraday's first law tells us that whenever the magnetic flux linking a closed circuit changes, an electromotive force, E.M.F, is induced in the circuit. Now let's break this down. A magnetic flux simply refers to the total magnetic field passing through a surface like a coil. A closed circuit means that current can flow if voltage is present. So, this law tells us that a changing magnetic field near a conductor causes a voltage to appear across it, and that can drive current. Think of a simple example. If you move a magnet towards or away from a coil, you'll see a small bulb connected to the coil glow. That glow is due to the induced E.M.F. Now comes the second law, which is more quantitative. Faraday's second law states, the magnitude of induced E.M.F is directly proportional to the rate of change of magnetic flux. This means the faster you change the magnetic field, either by moving the magnet faster or increasing the number of turns in the coil, the greater the voltage generated. Mathematically, it is written as A equals negative d phi divided by dt, where A is the induced E.M.F voltage, phi is the magnetic flux, d phi dt is the rate at which the flux is changing. The negative sign here comes from another law, Lenz's law, which we will discuss in the next slide. In real life, this principle is used in generators, transformers, induction cookers, wireless chargers. Understanding these laws is important because they explain how electricity is generated in all power plants, whether coal-based, wind, or hydro. Slide 2. Direction of induced E.M.F, Lenz's law and Fleming's right-hand rule. Now, even if we know a voltage is induced, we also need to know which direction the current will flow. That's where Lenz's law and Fleming's right-hand rule come in. Lenz's law says, the direction of the induced current is such that it opposes the change in magnetic flux that caused it. Let's understand this with an example. If you move a magnet towards a coil, a current will be induced. But this induced current creates its own magnetic field that tries to push the magnet away. This opposing behavior is nature's way of conserving energy. This is why there is a negative sign in Faraday's equation. It's not just a mathematical detail, it shows that nature resists change. Now, to determine the actual direction of current, we use Fleming's right-hand rule. Stretch your thumb, forefinger, and middle finger perpendicular to each other. Thumb equals direction of motion of conductor. Forefinger equals direction of magnetic field, N to S. Middle finger equals direction of induced current, E.M.F. This rule is especially useful in understanding how generators work. They rotate a coil inside a magnetic field to produce voltage in a specific direction. So, these two tools, Lenz's law for opposition and energy conservation and Fleming's right-hand rule for direction prediction, help engineers design efficient and safe machines. Slide 3. Applications and importance of electromagnetic induction. Let's now connect what we've learned with real-world uses. The principle of electromagnetic induction is everywhere in our electrical world. 1. Electric generators. They rotate coils in a magnetic field to produce electricity. Power plants use this principle to power homes and cities. 2. Transformers. These use changing magnetic fields to step up or step down voltages, for example, from 11 kV to 230 volts for household use. 3. Induction motors work using a rotating magnetic field to induce current in the rotor. This principle is used in fans, elevators, etc. 4. Wireless charging. Your phone can charge wirelessly because a changing magnetic field from the base induces current in the phone's receiver coil. 5. Induction heating. Cooking without fire. The coil underneath the induction cooktop induces current in the cooking vessel, which heats up. 6. Guitar pickups. Vibration of strings affects the magnetic field and induces current, which is converted to sound. 7. Eddy current brakes. High-speed trains use this to stop without friction. Induced current creates an opposing magnetic field that slows them down. 8. Magnetic braking in elevators. Safer braking by induction instead of relying only on mechanical parts. 9. Metal detectors. These detect changes in inductance when a metallic object is nearby. Each of these applications relies on the basic idea that a changing magnetic field induces a voltage, and understanding this helps us design and troubleshoot a wide variety of modern systems.